Go into the next topic with respective to the second module, which is pertaining with scaling and small geometry effects and along with MOSFET capacitances. So the purpose of this particular topic is we need to shrink the size of the IC. When you're shrinking the size, you have to have a different dimension. So the dimension exists as it is, but you have to scale it. You have to have a parameter which has to be scaled. Normally we write the scale on the graph. So 1 centimeter is equal to 10 volts or 1 centimeter is equal to 1 meter. But that doesn't represent that it is 1 meter. Then when you go back and scale up, you do the reverse procedure. If you have 5 blocks on your graph, it is nothing but 5 meters, because one block represents 1 meter. So this is how the scaling helps us, and we are all quite familiar by now, I hope. So we'll look into this topic now. Now we look into the next topic, which is layout dependence of capacitance. So what exactly is the impact of capacitance on the layout? In a good layout, diffusion nodes are shared wherever possible to reduce the diffusion capacitance. So when you look into the layout diagram, you can notice that the diffusion capacitance is shared, and as a result, the nodes are also possibly reduced. Therefore, the uncontacted diffusion nodes between series transistors are smaller than that which is contacted. So the possibility of looking into the layout is only to see how much of the capacitance is being shared, and such uncontacted. So avoid the contact, and once the contact is not allowed, you will have less capacitance. So a conservative method of estimating capacitances before the layout is to assume uncontacted diffusion between series transistors and contacted diffusion in all other nodes. So please note, whenever we have a series transistor, then the diffusion is uncontacted, and as a result there is no capacitance, or the capacitance is shared. Therefore you will have no more capacitances. Therefore this is a conservative method, but however we can accurately estimate how much can be looked when you look into the layout. So we have a layout representation. This is a layout of a 3-input NAND gate. So when you notice here, this is the shared contacted diffusion. So you can see whatever the diffusion exists between this and this, the same thing is being shared. It is being shared. So a single drain diffusion region is shared between the two of the PMOS transistors. You have two PMOS transistors, therefore it is being shared. Estimate the actual diffusion capacitance from the layout, and here you have merged uncontacted diffusion. So, and these are the isolated contacted diffusion. So you can see uncontacted diffusion helps us to have lesser capacitance. So with this diagram we go ahead. Shared contacted diffusion means contacted, it is in contact. Uncontacted where is the one which has lesser capacitance. So you can have a schematic representation. So when you look into this, the output node has the following diffusion capacitances. So we'll look into this: 3C from the NMOS transistor drain, 2C from the isolated PMOS transistor drain, 2C from a pair of PMOS drains that share a contact. So the contacts are reduced, and as a whole 3 plus 2 plus 2, 4, 5, 6, 7 is 7C. As earlier predicted, it was 9C. So you can look into this. Therefore this has been shared. Alright. So this happens to be 3C, this happens to be 3C, and instead of taking all, one is shared, right? So it forms 4 and 5, 6, 7. So together they form, the sharing is done here in PMOS, and that is how we have the capacitance as 7C when you look deeply or keenly inside the layout representation. Next topic of the day is the linear delay model. So what exactly we had all the while was the RC delay model. There the delay is a linear function of a fan out of the gate. So everything dependent, delay was completely dependent on the fan out of the gate. How much how much further gates or the logic devices can be driven. So based on these observations, designers further simplify delay analysis by characterizing a gate by a slope and y-intercept of this region. So that in RC delay model, it completely dependent on was depending on the fan out of the device. But in order to avoid that, a little more design was refined, and that was taken care with the slope and the y-intercept of this. So the delay of the gate is expressed. So keeping this in mind, and the delay is given by F plus P. So what exactly is F and what exactly is P? P is the parasitic delay which is inherent to the gate when no load is attached. So P is always present, which is the parasitic delay, and it is inherent. It's always present in the gate. Whereas F is called as the effort delay or stage effort, that depends on the complexity and fan out of the gate. So we have a new term being defined here, which is called as F, which is called as the effort delay or stage effort. This, in other words, is nothing but dependent on G and H. So where H is the fan out and G is the gate value. So depending on this, as already seen G from the previous topics. So this is the new delay which is present in the linear delay model. So the complexity is represented by the logic effort G. Okay, G here is called as the logic effort. And now we have an inverter is defined to have a logic effort of 1. So what exactly is J? As we go on, we will find out. So the inverter is defined to have a logic effort of 1. And if there are more complex gates having greater logic efforts, then they take longer time to drive a given fan out. So as much as possible, we need to have the logic efforts to be as less as possible or as minimal as possible. For example, you have the logic effort of a 3-input NAND gate. From the previous example is 5 by 3. So an example has been given for 3-input NAND gate. The logic effort is 5 by 3. And the gate driving H identifies copies of itself is said to have a fan out of electric fan out, or the electric effort is H. So H is nothing but the fan out, which is given by the ratio of load capacitance divided by the input capacitance. Yes, as it is given here. So if the load does not contain identical copies of the gate, the electrical effort can be computed as. So if there is no load, or it is not having any identical copies, then the load itself is considered as the output capacitance, which is divided by the input capacitance. As I have already defined, the value of H is the ratio of the load capacitance by the input capacitance. So now we have come across a new term called as G. G is called as a logical effort, and G should be as minimal as possible. For an inverter, it is defined to be 1. So the logic effort of a 3-input NAND gate is given as 5 by 3. Let us see if we have any further classes or the further slides will tell us how exactly 5 by 3 is got. So what is logic effort? Logical effort. Just now I told you G. Logical effort of a gate is defined as the ratio of the input capacitance of the gate to the input capacitance of the inverter that can deliver the same output current. So earlier we had the fan out H given as ratio of the output capacitance by input capacitance, but here the ratio is, but here logical effort is nothing but the ratio of the input capacitance to the input capacitance of the inverter. So equivalently, logical effort indicates how much worse a gate is at producing output current as compared to an inverter. So that should deliver the same output current. So therefore logic effort indicates, it tells whether the device is good in generating current or not based on the logical effort. So this can be measured in simulation from delay versus fan out plots as the ratio of the slope of the delay, etc. with the help of slope and using the simulation, the logic effort can be determined, or else it can be estimated by sketching the gates. So two possibilities are there to understand how in what way should we generate or should we calculate the logical effort. Okay, now we have an example where we understand what is G or the logic effort as. So figure shows an inverter Figure shows inverter 3. Okay, there are different devices, 3 input NAND gates with transistor widths chosen to achieve unit resistance, assuming PMOS transistors have twice the resistance of NMOS. So there is also another device which is an inverter, but right now what you can see is the 3 input NAND gate. So the width has been given here and widths chosen to achieve unit resistance. So assuming PMOS has twice, okay, the resistance in PMOS is unit. As I have told you, 2R by 2 will give you unit resistance, whereas NMOS will be R by 3. So the inverter presents 3 units of input capacitance and NAND gate presents 5 units of capacitance. Okay, inverter I will show you later on. Somewhere the slide has been missed. Let me check a little later. The NAND presents 5 units of capacitance on each input. So the logic effort is 5 by 3. So when you look in the input capacitance, gate input capacitance is how much? Input of 1 PMOS and 1 NMOS. Together this forms 2C, this forms 3C. So what is the input capacitance? 5. It is nothing but capacitance used in this logic NAND gate is 5. And what is the ratio? G. G is defined as ratio of the input gate capacitance divided by, previous slide we need to check, even I forgot, it should be logic gate. Okay, 5 you are familiar I hope right now. It is the input capacitance divided by the input something, diffusion capacitance or something. So that is nothing but 3. So let me put that slide here. I'll check with that. Therefore the logic effort is 5 by 3. Alright, I had to put the inverter first, but for some reason I just had a miss there, and I have explained about the NAND gate first. So this is the inverter, this is A, and the NAND gate was B. So the inverter presents 3 units of input capacitance. So when you look into this, this is commonly connected. Therefore this has 2C and this has 1C. Therefore the input capacitance is 3. And it is the ratio of input capacitance and the capacitance of the inverter. So how many capacitances are there of the inverter? A normal, this is a unit transistor. So this has 2C and this has 1C. The diffusion capacitance is 2C and 2C. So 2C plus 1C, sorry not 2C, 2C for the PMOS and 1C for the NMOS. Therefore it happens to be 3C. Therefore when Cin is equal to 3, G is equal to 3 divided by this 3. Therefore G is equal to 1. So please remember, in further cases we again keep on talking that the input resistance or input capacitance is whatever is the choice or the width factor given, but always the capacitance of the inverter is 3. It is constant because we are considering the unit inverter. So the inverter presents 3 units of input capacitance. Let us look at the next device. This is a 3 input NOR gate. So if you look at the 3 input NOR gate, this is of 6. PMOS is of 6 and the NMOS is of 1. So what would be the total input capacitance? 6 of one PMOS device and 1 of one NMOS device. Together 6 plus 1 makes it as 7. And the ratio of the inverter. What is the inverter capacitance? Always it is the inverter capacitance is 3. Just now I have defined. Therefore G happens to be 7 by 3. Now we have the list table of the logic effort of common gates. If you look into this, number of inputs are 1, 2, 3, 4 and n. If it is an inverter, so the logic effort of an inverter is 1 because 3 by 3 is 1, standard inverter. If you have an input of 2, if you have a NAND gate of 2 inputs, so 2 inputs in the sense 2 PMOS in parallel and 2 NMOS in series, therefore 2 plus 2 will make 4. 2 input NAND gate will make 4 and therefore divided by the inverter capacitance which is 3. 3 input NAND gate. So 3 plus 3 input NAND gate will be depending on the values width. What is the width? Depending on the width, the value of phi is considered. So if it is a 3 input NAND gate, we have seen 3 and 2. Size of PMOS is 2 and size of NMOS is 3, therefore it is 5. 5 by 3. So depending on whatever is the number of inputs, that is how, depending on the W factor, we have got these many values. So generally whatever is the N value, N plus 2 divided by 3. 3 is common, 2 is also a common value depending on the number of inputs. 4 plus 2, 3 plus 2, 2 plus 2, 4. So this is how we get the common logical effort for a NAND gate. And for a NOR gate it would be 2n plus 1. It gives you the number of inputs. So if you have 2 to the 4, 4 plus 1, 5, 3 to the 6 plus 1, 7. So this is how it has been generalized, and this is how we are able to calculate. So please remember, for NAND gate it is n plus 2 by 3, for NOR gate it is 2n plus 1 by 3. So the NAND gates are better than NOR gates because the series transistors are NMOS rather than PMOS. So in NAND gate what happens, the series transistors are NMOS whereas the PMOS transistors are in parallel. So when it is in series, any one can be considered, therefore NAND gates are better than NOR gates. If you consider exclusive OR gates, they are particularly costly and they have different logic efforts for different inputs. Little complicated. Since we are talking only about the basic gates, we talk in terms of inverter, NAND and NOR. Next, we have another type of delay which is called as parasitic delay. So what is a parasitic delay? A parasitic delay of a gate is when it drives zero load. It can be estimated with RC delay models. So we know when there is no load, we can simply merely consider the RC delay model. That helps us to find out what is the value of the delay. But a crude method which is good for hand calculations is to count only diffusion capacitance on the output node. So what is the diffusion capacitance on the output node? If this is your output node, the diffusion capacitance is 2 plus 1, 3. This is the crude method which helps us to find out what is the capacitance. So transistor widths were chosen to give a resistance of R in each gate. Yes, width value gives you the resistance value. So in this case, PMOS resistance is 2R. 2R divided by 2 will give you R. In this case, the NMOS resistance is R and the value width is 1. Therefore, R by 1 in turn is nothing but R. Now we consider an inverter with 3 units of diffusion capacitance. Yes, just now I told you the diffusion capacitance is hand calculation is to count only the diffusion capacitance. So 2 plus 1. Therefore, the diffusion capacitance on the output is 3. Therefore, what is the parasitic delay? The parasitic delay is given by 3RC. Whatever is the value of the capacitance on the diffusion side multiplied by RC, that gives you tau. So this is how a parasitic delay can be calculated. Now let us calculate the parasitic delay of different gates. So generally the normalized parasitic delay is 1 and is called as P inverter if it is an inverter. So P in V is the ratio of diffusion capacitance to gate capacitance. Yes, we have C in as 5, 2 plus 3, 5, and G is given by whatever is the input capacitance divided by the inverter capacitance, which is 3. So this is fine. Next, the 3 input NAND and NOR each have 9 units of diffusion capacitances. How 9? So when you look into this, diffusion capacitances, this is of 2, this is of 2, this is of 2. 2 plus 2 plus 2, because this is a common drain junction. It turns out to be 6. And you have only one NMOS transistor which has drain here. This is source, this is drain, this is source, this is drain. The connections are different. So we want purely drain terminals, therefore it is 2 plus 2 plus 2 plus 3, which turns out to be 6 plus 3, which is 9 units on the output side. Therefore the parasitic delay is 3 times. Again it turns out to be 3P inverse inverter or simply 3. So the parasitic inverter delay would be 3p inverter. In the second case, how much is the drain? Drain value is 6 and the drain value of the NMOS is 111. So 6 plus 1 plus 1, 9. 9. Here also. So the 3 input NAND and the NOR each have 9 units of diffusion capacitances. 9 units. But what is G here? The input capacitance is everywhere it is 6 plus 1, 7. 7 by 3. So the 9 units of diffusion capacitance on the output. So the parasitic delay is 3 times that of the inverter. 3 RC. 3 into 3 would give you 9 RC. So this is how the parasitic delay is calculated. So the table below estimates the parasitic delay of common gates. Increasing transistor sizes reduces resistance and increases capacitance. We have seen RC is there as the delay. If R value size is more, R value reduces and C value increases. But what is the relationship? Parasitic delay is on first order independent of gate size. But whenever we have wider transistors, it can be folded. So larger gates tend to have slightly lower parasitic delay. So ultimately we have to keep in mind the size of the width and the width especially, which is completely dependent on which gives you a value which is proportional to R and C. So appropriately you have to design the value of width because it is completely dependent on, it is completely having an impact on R and C, and R and C in other words is nothing but the delay. So designing has to be taken into point in terms of width.